Hello, ladies and gentlemen, this is Dean from AlphaPy, and this is Linear Algebra. Here I am on what is called matrixcalc.org, which is a very helpful tool if you are stuck doing any matrix equations. But we're not at that part yet. We're just in this so that I can type in matrices easily without having to do it in Paint. Anyway, we started by covering matrices and a little into vectors, and I'd like to pause for a second here to notify you of some special matrices. These matrices have special properties, mostly when multiplying, which is a topic for another video. This is mostly just to introduce you and catalog them for reference in later videos, as they are extremely important. For all these examples, I'll be doing 3x3 matrices, but they can be any n by n, so these matrices are always square. That is to say, they have the same number of rows as columns. First off, we have the diagonal matrix, which is a matrix whose entries are all 0, except for the ones along the diagonal. In matrices, we use coordinates I, j to place entries, where I is the place along its number of rows, and j is its coordinate of columns. In diagonal matrices, there are only II, non-zero entries. Keep in mind that 0 entries are different from empty or not a number entries because 0 exists. The identity matrix, which is a special diagonal matrix, whose entries are all 1, or at least its diagonal entries. This essentially is the matrix equivalent to the number 1 and will recur very often. The anti-diagonal matrix has entries along the other diagonal, which results in a different property when multiplying than a diagonal matrix. A symmetric matrix is one such that its transpose is equal to it. We'll talk about transposes more later, but they're essentially the mirror image of a matrix. Symmetric matrices are given by ABC, BAD, CDA. So you can see if you folded it like that, it would be symmetric, which is why they're called that. A skewed symmetric matrix is similar, but all the entries are made so that the transpose is the opposite of the original. Note that here all the diagonal entries have to be 0 because the only number equal to its opposite is 0. If you look at only one side of a symmetric matrix, you get what's called a triangular matrix, which has entries on the upper triangle, where the diagonal consists of all the same numbers, again, like the symmetric matrices. The lower triangle is the opposite, where it's the bottom of a symmetric matrix. Note that there isn't anything saying that A, B, and C in these scenarios are different numbers. But for each B has to be equal to B, each C has to be equal to C, and so on. The row operations have associated matrices, which are plays on the identity. In fact, they are the result of using the operations on the identity matrix. For example, swapping row 1 and 2 is associated with the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1. As you see, it's the identity matrix, but with the first and second rows swapped. Multiplying a constant k to a row, for example, the second row here, is associated as such. And adding a multiple of another row, example q row 3's to row 1, is associated like this. A 0 matrix has all 0 entries, and a constant matrix has all entries the same, which, as we'll see later, is a scalar, or I guess you could call it a scalar multiple of a 1 matrix, which is this, but all 1s. Also, remember that an arbitrary matrix is usually denoted by A, and we'll see this quite a bit when we talk more about equations. But when more than one is included, it's okay to use B, C, D, and so on, but just be sure to define it that way. The identity matrix is denoted by I, and it's common to use the matrix size alongside its letter. P and D also have special uses when we talk about eigenvectors and eigenspaces, but that's very late. Lastly, let's look at the cases of solutions. Sometimes you'll run into problems that include a variable within the matrix and are asked to come up with values for this variable such that the matrix has a single, infinite, or zero solutions. The idea here is to find the dimension of the solution and where it doesn't exist. As an example, I've come up with this one. And it's important to note that this is already reduced, but that might not always be the case, and is usually not. This is very gratuitous, and I've taken quite a few liberties on constructing it. The easiest case of solution is to find where it has no solution. And here we want to show that there is a non-zero third row entry in the augment, but the third row other than the augment is all zero. Here we have k is equal to -2 because -2 squared is 4 minus 4 is 0, but -2 minus 2 is -4. In this way, you're essentially saying that 0 is equal to -4, which is false. Because of that, this matrix would have no solution. Next, we'll look at how we can find where there are infinite many solutions. To find this value, we need to cancel the last row, or more if there are more, completely so that it becomes what's called a zero row, where it essentially functions like it doesn't exist. And in doing so, we're making a square matrix into a wide matrix. This way, we have a vector or planar or whatever solution, as we saw in the last video. To do this, we set k is equal to 2 in this case, because 2 squared minus 4 is 0, and 2 minus 2 is 0. So last row cancels, and we have this as 2 and this as 5, which becomes a vector. The last case is where there's only one solution, and we're going to look to find where constants allow for the reduction into an identity matrix. In this case, it's any value of k such that it's not equal to -2 and 2, so that the third row is non-zero and exists. This part of the answer is often constructed where you have one case that's only defined by an inequality, and to get it, you have to solve for the other two first.